Good morning, students. School list. I'm audible.
Yes, sir.
Good morning, everyone. So, sir is a little busy today, so I'll be conducting your class today. I believe that you had started a new topic yesterday. Is it so? हाँ, कल आपने कोई नया टॉपिक स्टार्ट किया था. I believe it's state feedback or poll placement of
Yes,
your
sir.
analysis. So, first of all, can anyone just quickly summarize what you have read yesterday's lecture? Anyone of you can just summarize a bit for me, so that we may build upon that. A quick summary. Yes. हाँ. Anyone? क्या पढ़ा आपने स्टेट फीडबैक फॉर्म में? अभी तक क्या पढ़ा आपने?
सर कंट्रोलेबिलिटी के बारे में बताया था सर.
ओके. उसमें क्या पढ़ा? नहीं, आई एम स्पेसिफिकली आस्किंग फॉर यस्टरडेज लेक्चर. अभी तक वो नहीं मैं पूछ रहा हूँ. जस्ट आस्किंग कि यस्टरडे जब आपने नया टॉपिक स्टार्ट किया है, उसमें अभी तक क्या पढ़ा नए टॉपिक में? दैट्स व्हाट आई एम आस्किंग.
सर एक सिस्टम अगर दिया है एंड उसका आइगन वैल्यूज एस प्लेन में कहीं पे है, अगर मुझे उन आइगन वैल्यूज का लोकेशन चेंज करना है तो हम इनपुट से हम चेंज करते हैं, ये कल कर देते हैं. तो वो इनपुट को -kx लेके हम सॉल्व करते हैं आगे.
Yes. Yeah, you can. That's a good explanation. A simple and good explanation. कि अगर आपके पास कोई सिस्टम है, intuitively, it's if you have a system whose open loop poles are like this, and ये जो आपने टॉपिक बेसिकली स्टार्ट किया है, this is more of a control perspective, क्योंकि अभी तक आपने जो concepts पढ़े हैं, then now you are going to use them basically. So now we are going to some practical point of view कि अभी हमारे पास एक सिस्टम है and we want to modify its behavior. We want let's say we want the poles or eigenvalues to be at some position that we want. So this comes under pole placement or state feedback analysis. ये जो है काफी तरीकों से किया जा सकता है. जैसे मैंने आपको लैब में भी पढ़ाया था. You can modify behavior of a system in many ways. There are many ways to do this, and one of the method is which is commercially used is the state feedback or the pole placement. इसमें क्या होता है? You can move any pole to any desired location you want, depending upon what you want to achieve. अब यहाँ पे there are some constraints, there are some hiccups कि आप सारे poles place कर सकते हो, कुछ poles place कर सकते हो. Do you have information of anything? वो चीजें बाद में आएंगी. But first you have to get very acquainted कि ये pole placement है क्या, and how do we basically do this, and what are the, if we do this, what are the repercussions? Do we have any? So today we will just build upon जो कल आपने introduction लिया था, and we will try to do a little example in which we will just place poles, and we will use some advantage from the knowledge we already have. So if I just, before we take the numerical or before we take the example, if I just summarize yesterday's lecture, if we had a system ax plus bu like this, okay, even sir may have told you yesterday the essence of this A and B. This A matrix is हमने start से पढ़ते आ रहे हैं. This A matrix tells how your system evolves, how your states are related with their derivatives, and this B tells you how your state affects the inputs or how the input affects your states. So if you want to design a controller, the controller has to essentially modify this A, because this A is a system property. The stability, the dynamics are all governed by this A matrix. So any controller that you want to wish to use, that should essentially modify this A. And how do we do that in state feedback? We use the control log given as u is equal to minus k times x. This is a very simple linear control that we can use, because this is a linear combination of x that you are injecting with some gain, and that's negative. Now, when you use this control law in your state space model, what you get? You get some modified version, a minus bk, isn't it? X. यही मिलता है ना आपको. When you substitute u as minus kx, you can take x common and you will get this new modified a. So if you look at this equation, this is what? This is a new matrix in unknown k. So if you can change this k, you can modify the behavior of the original plant, and that will be given by this a hat. And for this system, for the original system, if I talk about the original system without any modification, its characteristic polynomial is given as si minus a equal to 0, isn't it? This is the characteristic equation for this original system. And if we talk about this modified version now, its characteristic equation is given as a minus bk, determinant of this equation equal to 0. This is the characteristic polynomial for this modified system. तो ये चीज आपको सर ने आई गेस कल इंट्रोडक्शन में बताया होगा कि how if we use this control law in the original system, our system gets modified and the new characteristic equation becomes this. Now this is a polynomial in k, unknown k. When you expand this polynomial, the only unknown here will be k. Okay. So now we have done this. अच्छा आपको दिख रहा है कि it's, I guess it's, आपको बोर्ड दिख रहा है?
क्लियर नहीं आ रहा है.
हाँ, क्लियर नहीं आ रहा है. Wait a second, we'll just change some settings. So just hang on. Is it okay now? Are you able to see the board?
No sir, उसी तरह है.
Okay, just wait. Is it clear now?
Yes sir.
Huh. So tell me if you are having any difficulty in audio or video, just inform me, because otherwise I'm continuing. Okay. So ये तो basics हैं कि we do this, and how does this help our problem? If we do this, how does it help us? See, if you want your eigenvalues to be at some desired position, अब वो desired positions कहाँ से आएंगे? That's a separate topic. That is basically depends upon your design criteria. But let's suppose for now that we have some design criteria in mind, and we want our system to follow that, or we want our eigenvalues to be at those positions. So if we have, let's suppose, a desired pole locations, later on we will see how do we make these desired pole locations. Let's suppose for now you have them. You have as lambda1, lambda2, so on up to lambda. And these are your desired poles or desired eigenvalues, which you want the system to be. So if you're having this desired pole locations, what will be the desired, what you call characteristic equation then for these set of poles or these set of eigenvalues? It will be s minus lambda1, s minus lambda2, so on up to s minus lambda n, isn't it? This is your desired characteristic equation for these desired set of eigenvalues. Now, if I call this equation number 2, and I call this equation number 1. If I compare this equation with this equation, this is also a polynomial. This is also a polynomial. And when I expand this for an nth order system, you will get terms corresponding to S1, S2, S3, up to so on, Sn. Similarly, here you also have S1, S2 when you expand this. So what you can do is by just comparing the coefficient, just आपने last time शायद एक numerical भी किया था, I believe. If you compare the coefficient of S here and S here, let's suppose you compare the coefficient of S1 from this and from this, you will get one value of K. Then if you move on and compare the coefficient S square from this equation, you will get another variable of K, because this K is basically like this. it's K1, K2, K3, so on. It's also इसके entries भी n होंगे. So ये जो control law है, the only unknown in this control law is this vector k. So for these constants, what you can do, you can just compare the coefficients, and one by one you will get these constants. अभी मैं बस theory बता रहा हूँ. When we go to examples, will be much more clear. This is a general idea. How do we do this? We have a system. Let me repeat. We have a system. We use this control law. We modify its behavior, and now our characteristic equation becomes this. This is equation. I'm sorry because we just lost power and I just got disconnected. So I'm audible.
Yes, sir.
Okay. So what I was saying, if I just quickly summarize that, we have one equation corresponding to this. This was the equation 1. This you get from substituting u is equal to minus kx in the original system. The second equation जो आपके पास थी, that was in lambdas, s minus lambda 2, so on up to s minus lambda n. This is equation 2. If you compare both the equations component wise, that's you compare the coefficient of s1, s2, s3 up to sn, you will get your k1, k2, k3 up to kn. This is a general approach how we place the poles. We'll come to an example, so just hang on. This is a general approach, but let me tell you one thing. This is the system that we started with, and this is the modified version, isn't it? यहाँ पे क्या है? This is a modified A. The whole यहाँ पे जो effort लगता है for placing these poles and finding these coefficients is finding this matrix A minus BK. है ना? जो आपका new modified A है. The whole effort goes into finding this A minus BK. And let me tell you, for systems which are high dimensional, let's यहाँ पे तो मैंने n ले लिया. I assumed here n states, or n is the dimension of the state space model. If you're having model जिसमें n का order हो जाता है, let's suppose 10, 12, 13, the finding this A minus BK becomes very cumbersome. because let's suppose you have a model n is equal to 13. ठीक है, स्टेट स्पेस का मॉडल आपका 13 है. एक ऐसा मॉडल है जिसमें 13 स्टेट वेरिएबल्स इंक्लूडेड है. So when you say n is equal to 13, so this equation will having how many poles or how many solutions to this equation equal to 0? You'll be having 13 for this and 13 for this. So you can go component wise and find 13 constants for this k vector. So this computation becomes difficult, a minus bk, for a general class of systems. So what we do is we exploit some properties. जैसे मैं अभी तक कहता आ रहा हूँ कि we use some system theoretic properties or some very special. क्योंकि हमने अपने start के lectures में canonical models पढ़े हैं. We have talked about canonical models, and why we talk them canonical, because there are some special models. So we can exploit the property of canonical model to solve this problem. First of all, ये तो समझ में आ गया कि हम कैसे निकालेंगे these gains. For a general system, for a general system, we'll just compare the coefficients. But the issue is that this a minus bk requires a lot of effort when n goes very high. So we will just exploit a property of a companion model in which this equation becomes very easy to solve. It's a minus bk. What we do is we will use following. Acha. If we talk about companion model, the first companion model is called first canonical form बोलते हैं, or sometimes we call it controllable canonical form also. You may have realized that. So you know a property of the first companion form, that if you're having a state space model which is in the first companion form or the controller canonical form, you may be also knowing that if you're having a system in this form, you don't have to apply any controllability test for the system. Why we call it a controllable canonical form? Because this is guaranteed to be controllable. Do you know that?
Yes, sir.
Other system, I will repeat. If you have a system represented in first companion form or controller canonical form, this system is guaranteed to be controllable. You don't have to test it whether it's controllable or not. This system is guaranteed to be controllable. Conversely, I can also say that if a system is already controllable, using some test, we find out the system is controllable, then that system can be easily transformed to first companion form. I'm just using two different statements for the same fact. If a system is in first canonical form, which means it's controllable, or if a system is controllable, we know it, then you can transform it into first companion form. This is a fact that you should remember. Now, we will use this canonical form for pole placement. See what we will do. अगर आपके पास कोई controller canonical form है, and you know, you're very much aware of controllable canonical form, this A matrix looks like this for a controller canonical form. We will use the same notation जो सर ने क्लास में यूज की है. It's 0 minus alpha n. It's 0 minus alpha n minus 1. It is minus here 1. यहाँ पर एक 1 होगा. This 1 ऐसे 1 चलता है, and you have minus alpha 1. है ना? This is the A matrix for the first companion form, if you remember. अच्छा, how does B look like in the first companion form? It's simply 0, 0, 0, and 1. We will exploit this first companion form for pole placement. That's what I'm going to do. So what's the advantage here? Advantage for this A is a special A, it's a canonical A, is that it's having 1 on the upper diagonal. Yeah, which 1 hand that's on the upper diagonal and rest are zeros. And the denominator is already having the coefficients for the characteristic equation, if you remember. यहाँ पे जो है जो basically जहाँ से हमने start किया है to build this canonical form, the denominator है, that's very special in this. This denominator are basically the coefficients of your characteristic polynomial written in the reverse order. So what's the advantage here? Advantage is if you do A minus bk here, जो A minus bk हमें करना पड़ता है for pole placement, that becomes very easy. How? यहाँ पे क्या होता है? We'll just use different color to just highlight यहाँ पे क्या advantage है. यहाँ पे जो आपके पास k है, k1, k2, so on up to kn, जो आपको find out करने होते हैं. If you have a system already in first controllable canonical form or which is already controllable, what you can do is you can easily find this case. और जो मैंने आपको दिखाया था A minus bk, that comes out to be this. यहाँ पे K1 subtract होगा, यहाँ पे K2 subtract होगा. I'm talking these K1, K2s, and यहाँ पे जो है Kn subtract होगा. And this is not A now. This is an A minus BK matrix. This is that I want to convey to you. Please understand this. This is very important. If you are having a system which is in a first companion form or a controller canonical form, whose A matrix is similar to this, you can straight away write A minus BK, which is again the same matrix. The only change is in the denominator, the coefficient of जो आपके पास alpha n है, you subtract the first K1, जो first entry है of your controller. Then subtract second entry from this, subtract so on, and last entry will get subtracted by Kn. और हम क्या करते थे in state feedback? Once we found this A minus BK, what was the next step? We compared it with our desired characteristic equation. तो यहाँ पे जो ये है, this term, this is the coefficient for the constant term. Just bear with me, I will explain. This is the coefficient of S. Moving so on, this is the coefficient of S to the power n minus 1. Let me say what I have written here. First of all, I just told you कि अगर कोई system है, A minus BK is very easy. You just subtract these constants in the denominator. Then what you do, when you compare your A minus BK, Si minus A minus BK, when you compare this equation, if you remember, we compared it with our desired value. This is our desired poles. This is the last step of pole placement to find these gains. अगर आप compare करने वाले हो, तो ये तो आ गया मेरे पास A minus B के matrix I found out straight away. तो ये वाली term होगी. You compare this with the constant term from this equation. You don't have to take exactly this. You have to take negative times this. If this is minus alpha n minus K1, you will compare alpha n plus K1. Negative of this, because if you remember, जो first control canonical form में लिया था, हमने एक तो reverse में लिखा था, and we have written with a negative sign. So you have to take care of both the reverse order and the negative sign. So this is the term which will be compared to the constant term of this equation. This is the term which will be compared with the term of s to the power 1. Then the next term जो भी होगी, that will be compared with s1. No, sorry, s2. Next term will be compared with s cube, and so on. And the last term होगी, that will be compared with s to the power n minus 1. तो इस सिस्टम के लिए पोल प्लेसमेंट काफी इजी हो जाता है. You don't have to evaluate A minus BK, then determinant of that putting equal to 0. You can straight away write A, use the coefficient, subtract K1, and simply. अच्छा, आपने इस पे एक numerical भी किया है कल. If you remember, if you go back to your notes, just go back to the example जो आपने last time की थी, जो सर ने आपको 3/3 की example दिखाई थी. Just see कि उसमें जो A minus BK है, उसमें denominator क्या बना था? Just see from your notes, जो कल की example ली थी हमने, सर ने कराई थी, उसमें जो A minus BK था. अच्छा, जो example दी थी, that was first of all in control canonical form, है ना? Are you following?
Yes, sir.
Yes, sir.
उस एग्जाम्पल को देखो, just look at the denominators. वहां पे आपको similar kind of equation मिली होगी, alpha n minus k1, alpha n minus k2, and उसके बाद क्या किया होगा आपने ये compare किया होगा with the constant term, ये compare किया होगा with s term, ये compare किया होगा with s square. वहां पे तो तीन ही terms थी, तो constant term, s term and s square term होगी, बस तीन terms होंगी वहां पे. तो आपने straight away compare किया होगा और आपको k के values मिले होंगे, k1, k2 and k3. So this becomes easy now. If you have a system in this form, you can do this. If you don't have system in this form now, let's suppose you don't have this system. So what you will do? तो आप general approach करोगे. आप A minus B के find out करोगे. For that system, आप इसका equal to 0 करके इसको expand करोगे. Then another system will come from your desired, and then you will compare and you will get K. So an example that I will show you right now, उसमें हम क्या करेंगे? I will give you a general A matrix, which is not in first companion form. It's a general state space model. We will convert that system into this form. Okay, we will convert this system into first companion form. Then once we convert it into first component form, the calculations becomes easy. Then we solve everything in this first companion form, and then I will show you what is the advantage in the example. आपको ज़्यादा अच्छी से समझ में आएगा, or how we find out this case and how we say control law for this system. यहाँ पे मैं कुछ ताकि आपको कुछ कंफ्यूजन ना हो, या अगर आपको कुछ लग रहा है कि नोटेशंस में ज्यादा हो रही है, मुझे शो यू डायग्राम. उस डायग्राम से आपको काफी चीजें समझ में आएंगी. See, let's suppose you have a system. A general system, and just bear with me. You're using a control law, u is equal to minus kx. When you substitute in this, what you get? You get this? Okay. Now, just listen. I will use the state transformation. X equal to pz. I am using the same notation जो class में use होती है. What I am doing here is I am just changing the coordinates. Here the coordinates are x. है ना, यहाँ पे जो state variable है, that's x. I am just changing these coordinates. I am changing the coordinate from x to z, and the matrix or the basis that helps me to do that is this p. So p changed my x to z. When I do this, I get z dot is equal to, if you remember, p inverse ap z plus p inverse bu. Okay. This is my transformed state space model. Model तो same है, बस interpretation दो है. This is in x, this is in z, and moving from x to z, I require p. Okay, and if I am showing arrow like this, I can also show another arrow like this. Just focus on these arrows. If you want to move from x domain to z domain, or x directions to z directions, you require the transformation x equal to pz. If you want to move from z domain to x domain, or z coordinate system to x coordinate system, you will require the transformation z equal to p inverse of x. I'm just showing you the arrows. अब तो ये एक domain हो गया जो हमारा original है. अब I have shifted my system to this. What I can do here? यहाँ पे भी I can apply control law. अब यहाँ पे x नहीं होगा, यहाँ पे z होगा, क्योंकि यहाँ पे we talk about z, here we talk about x. यहाँ पे जो हम usually जो apply करते हैं, u is equal to minus kx here, है ना? यहाँ पे मैंने I'm talking about this. I have talked u is equal to minus kx. Can I write this minus k instead of x? I can write pz, and I am using this transformation. So this becomes my k dash. I can write this u is equal to k dash z. So this is k dash, not k. Because k is I am using in x domain or x coordinates. K dash I am using in z coordinates. So this is one and the same thing. यहाँ पे जो k होगा, that is k1, k2 up to kn. यहाँ पे जो k dash होगा, that is k1 dash, k2 dash, so on up to kn dash. Where kn and kn dash are the gains for both the control laws. ये मैं रख कर रहा हूँ. If I use now this control law, this is the control law in the transformed coordinates. I am using this control law in this equation. In this equation, what I will get? I will get z dot is equal to a dash, and one more thing, this I can write as a dash, and this I can write as b dash. So as to make it comparable with a and b, I'm having a dash, b dash, and k dash. So here I can write a dash minus b dash k dash times z. Are you following?
Yes, sir.
हाँ, तो इस डायग्राम पे फोकस करो. इस डायग्राम से क्या होगा? You will just आपकी डाउट्स अगर होंगे, you will get clear. Original system, x in x coordinates, I using a control law, I get this modified a. Now what I do, I've just done a change of bases. I've just shifted my coordinates to this using x equal to pz. I'm having this equation now. I'm using another control law in this coordinate system, u equal to minus k dash z, where k dash was जो मैंने यहाँ पे लिखा था k1 dash k2 dash, this is your k dash up to kn dash, and this is transposed. P. So if I use this here, I get another modified version of this, where this modified is given as a dash minus b dash times k dash, much similar to what's here. बस यहाँ पे difference है कि I'm using a z. तो ये तो है, this is just to give an idea कि how we do change of coordinates from this to this and how we can do change of coordinates from this to this. ये आपने पढ़ा होगा. Now we will use the property जो मैंने अभी बताई, controllability की. Because ये p कहाँ से आएगा and which coordinate system I use? I can have n number of coordinate system given by different values of p. Which coordinate system should I use? I will use that coordinate system which transforms my original system to canonical forms. That's what I'm interested in. I want the original system to get transformed into some special canonical form. And in this case, it's a first companion form. So I'm having a special transformation P matrix, which transforms my system to companion form. And once you get here, you will naturally see A dash, B dash will be the matrices corresponding to first companion form. So, दूसरी diagram देखो आप. Let me again write your original x dash equal to ax plus bu, and u is equal to minus kx. Okay, I'm using x equal to pz, and you will get z dot equal to a dash z plus b dash u, and u is equal to minus k dash z. Just correct me if I just use a different notation अगर मैंने कुछ किया. अच्छा, ये मैंने अभी समझाया आपको. Now tell me, in this original system, and this is let me say transformed. I'm just writing here transformed coordinate system. Can you tell me for this system what is the controllability matrix for this system? जो आपने पढ़ा होगा UCX, it's B, AB, A square B, A to power n minus 1B, isn't it? This is for the original system. है ना? And I believe you are written it as UCX. Coming on to this transformed system, what will be the controllability matrix for the transformed system? For the transformed system, simply B dash, A dash B, A dash square B, up to A dash n minus 1 B dash. This is dash. Everything is in dash version. And this is your UCZ. This is an X coordinate system. This is a Z coordinate system. This corresponds to this system. This corresponds to this system. Okay. Do you have any relation between the two? जो कल के class आपने derive की थी. Any relation between UCX and UCZ in terms of this P? And I can always write this. Now going back, I believe you have read this. Your UCX is equal to P times UCZ. ये आपने कल derive की थी ना equation. Just check the notes. Do you have this equation UCX is equal to P times UCZ?
Yes, sir.
ये कल derive की थी. This is again, if you see, this is again following this. If you are changing from X to Z, you'll be using P. If you're transforming from Z to X back, you will use P inverse. So the condition is that the P should have an inverse. अगर ये inverse exist नहीं करेगा, you cannot go back and forth. So the condition on this change of basis matrix is that you should be having an inverse. So this is if you transform UCX to UCZ, you just multiply with P, and you can do the reverse also. Then P inverse will come out. ठीक है, ये पिक्चर से आपको क्लियर हो जाएगा कि हम क्या करने वाले हैं. So again, I will use this. If you have a given system, similar diagram में बना रहा हूँ, and you're having a controller canonical form. Controller canonical. Your given system is x dot equal to ax plus bu, u equal to minus kx. I'm again repeating various things. X equal to pz, Here you have z dot equal to a dash z plus b dash u, and control law is minus k dash z. Okay, so UCX, like I said, is P times UCZ, where UCX and UCZ are controllability matrices for both the systems. ठीक है. अच्छा, यहाँ पे एक important fact है जिसके लिए मैंने ये यहाँ यूज किया. यहाँ पे यहाँ control law this, यहाँ control law this. Can you relate these two? यहाँ पे just find out first P. What's the value of P here? UCX, UCZ inverse. This immediately follows from this. Okay. So can I write this? Can I write this? Or can I write this? Can you follow this equation? हाँ, इसमें कुछ डाउट है? First of all, ये तो अभी हमने कल भी derive किया था. This follows from this. So can you write this equation? K dash, which is this, is K times P. Because your X and Z are related by this equation, so you can immediately say this. And from this it follows this. ये मैंने क्या लिखा है यहाँ पे? ये basically जो आपके gains है ना, K क्या है? K and K dash क्या है? K is the gain for controllability law of this system. K dash are the gains for the controllability law of this transformed or controlled canonical form. Now, how are this K and K dash related? That's related by P. You know, every entry from this system will be related to every entry of this system only by this P. क्योंकि हमने ये transformation use की. So यहाँ से ये पता चलता है, if you have a control law which you have find out here, this K dash, if you have find out a control law for this system, you can find a control law for this system if you know P. And converse is also true. If you have a control law which you have found out here, then you can immediately find a control law in this if you know P. ये जो है, ये property you will use in our numerical. Just write a numerical. Just simply write a numerical. Or I will just write some statements first. I will write ताकि आपको आसानी हो जाएगी. Just mention this. Pole placement algorithm. Just mention the steps. These steps हम करेंगे use. We will find the control canonical form because of the reasons I mentioned. Z dot equal to a dash z plus b dash. We will find this, and we can easily find this. अपने इसमें numericals लिखे हैं. Second is we will find pole placement, state, feedback for controller canonical form, that is u is equal to minus kz, k dash z, and remember these notations. This is your step 2. Step 3, you will find controllable matrices UCX and UCZ. Step 4, you will find transformation matrix using controllability matrices. Which is P, जो मैंने अभी दिखाया, UCX, UCZ inverse. ये वही steps हैं जो अभी अब तक हमने किए. I'm just summarizing all the steps. And final step, find state feedback for original system using k equal to k dash p. See, जो अभी तक मैंने आपको समझाने की कोशिश की है, just enlisted it in these 5 points, and this follows from the previous diagram. हम क्या काम करेंगे? We will find the controller canonical form. See, I'm just moving back to this diagram first. Our control problem will start like this. We will be given a system, and हमसे कहा जाएगा ये system है, just place your poles at these values, lambda n. This is the control problem. Place the eigenvalues of this matrix at this system at these desired pole locations. What we will do? We will not solve this. We will transform the system into controller canonical form, because I told you the advantage of this. यहाँ पे a minus b के find out करना आसान है. First step is to transform this system into this system to get a dash b dash. This is your step 1. जो मैंने लिखा. Find controller canonical form in this. Then what we will do? We will find pole placement in this coordinate system. We will find the pole placement this law here. Okay, then we will find the controllability matrices, this UCX and UCZ. ये हम find out करेंगे. अच्छा, you have to keep in mind, if you find your control law here, that doesn't mean you have find the control law here. क्योंकि यहाँ पे control law की definition is different, यहाँ पे control law की definition different है. यहाँ पे you are using gains k dash, यहाँ पे gains you are using k. So if I have initially transformed into this coordinate system, I am solving everything here. The last step is, if you have k dash, the last step will be to find out k, because this k will be used here. You cannot expect to use k dash here. You have to transform back or project back to get k. That's the last step. वही मैंने यहाँ पे लिखा. See, find control canonical form. Find pole placement feedback for controller. अभी तक हम controller canonical form में ही हैं. We will find controllability matrices. We will find the transformation matrix P. जब तक fourth step तक हमने K find out किया होगा. The last step will be to find state feedback for the original system. This is the important step. जब आपको K dash मिला होगा, तो original system के gains will be placed by this transformation. Okay, these are the 5 steps. Now everything will be clear if you take an example. Just as an example, or to make things simple, we will use a 2x2 example. Because we are interested here to just learn the basics, not develop into more computation. Let's suppose this is a system. And your C is 3, 4. This is your system. And the problem is, for the system, find k to set the poles at -1 and -1. Find k to set the closed loop poles at these locations. This is your control problem, and I have taken a 2x2 specifically for this problem, ताकि आपको चीजें से ज्यादा समझ में आए. But यहाँ पे एडवांटेज ये है कि we are using this जो मैंने अभी algorithm दिखाया. तो प्रॉब्लम समझ में आ गई. Given a system, find a k to move your poles to these specific locations. So if I go step by step, what was the step 1? Just read from the algorithm. Step 1 क्या था? Find the controller canonical form, isn't it? कैसे पता करेंगे? आपने assignments में भी किया. You एक given system को transform किया into companion forms. What you will do? You will find the transfer function. है ना? If you know the transfer function, you can move. You can write any canonical form from the transfer function. Find out this. See, assignments A inverse into B, and this is inverse. For 2x2, it's very simple. Let me write it. The answer. -5s plus 9.2 s square plus 1.4s plus 2.4. ठीक है? ऐसा माइनस a कर लो, फिर multiply by c, post multiply by b, you will get this transfer function. It's a second order transfer function corresponding to second order a. यहाँ से आप can you find out this first canonical form? Step 1 was controller canonical form. ये था ना first step. Tell me what's A dash. And please stop me if you're feeling कहीं पे समझ में नहीं आ रहा है. 0, 1, minus 2.4 and minus 1.4. Okay? This should be very comfortable for you. यहाँ पे strictly proper नहीं है, तो minus 2.4 with a negative sign, minus 1.4 with a negative sign. Reverse order. What's B? B is 0, 1. तो very simply first step हो गया. System को हमने एक कंट्रोलर कैनोनिकल फॉर्म के फॉर्म में लिखा by finding first the transfer function. ठीक है. What's step 2? Yes, what is step 2? Yes, I need some help. What is step 2?
So peak placement state feedback.
So just respond now. Step 2 is to define the feedback for control canonical form. See, desired poles क्या है? Desired poles are -1, -1. ये ना? तो desired polynomial क्या बनेगी? S plus 1 S whole square. ठीक है? और S square plus 2S plus 1. This is your desired polynomial in S. ठीक है? इसको मैं लिख लेता हूं as 1. Okay, tell me step 3. You have to find the controllability matrices. पहले हम ये सारे स्टेप्स कर लेते हैं, then I will just tell you little bit कि इसमें क्या करना था. Controllability matrices, find. You need UCX and you need UCZ. Now UCX is what? B and AB. What is UCZ? B dash, A dash, B dash. ठीक है? So what's B? Question में जो B given है, help me. What's B? हाँ. Roll number 2. Roll number 2. Are you with us?
So 0, 1.
हाँ. B. B is not 0, 1. I'm asking what's the first entry here.
1 minus 2.
Yes, B is 1 minus 2. What's AB? आपके पास A है ना of the original system. Multiply that with this 1 minus 2. Okay, I've written it here. Tell me for this. For UCZ, what's B dash? You know UCZ is control canonical form, which B dash is always 0, 1. Isn't it? Control canonical form में B dash is always 0, 1. What will be A dash, B dash? Again, very easy. Take this second column of A, because A dash, B dash is A, whatever A dash is, multiplied with 0, 1, which means you're extracting the second column. What is the second column? 1 minus 4. Minus 1.4. And everything becomes simpler in control canonical forms. यहाँ पे you have to evaluate AB. यहाँ पे AB is very much easy. There's this last column. So this is your UCX, this is your UCZ. Are you following? What's the step 4 now? What is step 4?
Finding P.
Yes. Step 4 is you have to find the similarity transformation matrix. P, which is your UCX, UCZ inverse. You have find out UCX, UCZ the previous step. Tell me P. 1 minus 2, 3, 1.8. times your 0 1 and 1 minus 1.4 inverse. Can you do this? Yes or no? Can you do this?
Yes, sir.
तो बताओ जरा मुझे ये इसका इनवर्स देन प्रोडक्ट इसका कर लो इसके साथ. Tell me this pretty fast. यही आ रहा है. This is your P. For a 2 by 2, it's simple. Inverse and then product. This is your P. I have completed step 4. Moving on. अच्छा, I believe step 2 जो है, step 2 we just didn't complete it. Step 2 में बस हमने we just found out this desired pole locations, but we didn't. जो मैंने step 2 लिखा था, if you see, I wrote step 2. Find pole placement state feedback for controller canonical form. U is equal to minus k dash z. We haven't अभी तक हमने ये नहीं किया. Step 2 में you have to find this. We just stopped here. So यहीं पे मैं लिख लेता हूँ. This is continuation of step 2. Moving it a bit here. This is from step 2 because we stopped in the middle from step 2. You have to find a dash minus b dash k dash. If you remember, तो मैंने कहा था ये है इक्वेशन जिसमें ज्यादा एफर्ट्स लगते हैं और इसलिए हमने ट्रांसफॉर्म किया ताकि ये इक्वेशन आसान हो जाए. तो वी आर इन कंट्रोल कैनोनिकल फॉर्म. मैंने दिखाया कंट्रोल कैनोनिकल फॉर्म में कैसे लिखेंगे दिस मैट्रिक्स, दिस इक्वेशन a minus b dash k dash 0 1. Everything remains same except the denominator. Minus 2.4. Minus 1.4. This was your a dash, है ना? This was your a dash. Now, if you are subtracting b dash k dash, क्या होगा? Minus k1 dash, यहाँ पे minus k2 dash. ये मैंने कहा था ना? Denominator में first entry subtract करो, इसमें second entry subtract करो. Now, si minus a dash minus b dash k dash equal to 0. This equation, this matrix. We'll get simply, मैंने कहा था this is your corresponds to constant term, this corresponds to s term, है ना? इसी तरह आगे फिर s square s cube की terms, यहाँ पे s पर stop हो गए. This is a 2 by 2 system. So क्या है ये equation? si minus a minus b के s square plus यहाँ पे कुछ s term होगी and plus some constant term होगी equal to 0. So s क्या मैंने कहा? This term, but it in a negative term. 1.4 plus k2 dash, and this term is corresponding to constant term within negative sign. मतलब negative को आपको account करना है. 2.4 plus k1 dash. ये करने के लिए हमने ये सारा algorithm यूज किया कि आप a minus b के easily find out करो. तो easily find out हुआ if you are having a and b as first control canonical matrices. ठीक है? This is your equation 2. Now compare 1 and 2. Comparing 1 and 2, we get what was your equation number 1? Equation 1 क्या लिखी थी हमने?
एक्सप्रेशन का होल स्क्वायर
S square plus 2s plus 1 equal to 0. यही था ना equation 1. And this is your equation 2. This one. Compare and tell me k dash. Coefficient s यहाँ से ले लो, coefficient of यहाँ पे what's the coefficient of s? 1.4 plus k2 dash. So 1.4 plus k2 dash should be equal to वहां पे जो coefficient of s है, that's 2. यहाँ which gives what? k2 dash as what? k2 dash कितना आएगा? 0.6. Now compare here constant term. Constant term is 2.4 plus k1 dash. वहां से constant term कितनी है? 1. That gives you k1 dash. How much? Minus 1.4. So your controller for the controller canonical form, that's k1 dash, k2 dash, which is minus 1.4.6. तो ये मैंने gains find out कर लिए, but remember this gains जो है, this is valid for controller canonical form. मतलब ये जो हम controller use करेंगे, ये controller मैंने find out किया for the controller canonical form, not for the original system. Original system में you don't have k dash. Original system में you have k. So that's why we require the final step, the fifth step. Step 5 is what? You will find your state feedback for original system. That's where we back project. Remember मैंने x to z दिखाया था? Then we can go from z to x. यहाँ पे हम वो यूज करेंगे. Your k जो आपको actually find out करना था, that's equal to k dash p inverse. You have everything? I can write this as k1 k2. I can add this as k1 dash k2 dash, and ये तो है ही p. Minus 4.41 minus me. What was your p? हाँ यही है. Minus 2. इसका inverse. k1 dash हमने find out किया minus 1.4. k2 dash हमने find out किया in the previous step 0.6. So can you tell me k1 and k2? If you solve this, minus 0.43 minus 0.517. This is your gains for your original system. And if you use these gains, you can see your poles will lie at minus 1, minus 1. Any questions in this? I expect कुछ questions आने चाहिए. Any question in this? Because this is important. कोई step में कोई confusion, हमने 5 steps लिए. Any confusion in any step? या हमने algorithm क्यों apply किया? What's the motivation for using such algorithm? And how did we apply it? If I move back to this, यहाँ पे मैंने diagram बनाई थी. That's more important. This one.
सर वो k dash equal to kp वो आया कैसे?
Okay. I will just look at this equation. हमने क्या काम किया था? I will just repeat for you. Just summarize the end of this lecture. We were given the system, and we were asked to place the poles of the system at some desired locations. Okay. हमने क्या काम किया? We transformed the system into controller canonical form using this P. ठीक है? हमने इसको transform करवाया into this. Then what we did? For this system, यहाँ पे चीजें आसान हो जाती है. ये जो है ना, ये जो motivation है, this motivation comes from very जो हमारे mathematical tools हैं. जैसे मान लो आप Laplace transform करते हो. आपके पास कोई सिस्टम होता है, you transform Laplace दूसरे कोऑर्डिनेट सिस्टम में जाते हो, वहां पे क्या है, वहां पे चीजें आसान होती है. Laplace में आपके डेरिवेटिव्स इंटीग्रेशन आसान है. या Fourier transforms another transformation. Fourier में भी आसान हो जाता है to find derivatives and integrals. This is much similar to that. हमें ट्रांसफॉर्मेशन कर रहे हैं and यहाँ पे चीजें करना आसान है because this is in control canonical form. That's why we chose this transformations, this special canonical form. So you transform the system using P to this. यहाँ पे you found out this U is equal to minus kz. क्योंकि यहाँ पे A minus B की find out करना काफी easy है. And यहाँ पे because this A dash and B dash and K dash. ये सीधे आपके मैट्रिक्स के जो मैट्रिक्स है उसके डिनोमिनेटर के पोल्स बस चेंज करना है, उसमें सबट्रैक्ट करना है. You can easily find out K dash in this. But the only hiccup is this is K dash I found out. The final utility will project back your K dash to find K for this system. That's the idea. This is the idea कि हम कर क्या रहे हैं. Now you ask कि ये equation कहाँ से आ रही है? ये पूछ रहे हो? How is K and K dash related? हाँ sir. You can use this equation now. X is equal to PZ. you know relation between this system and this system. The relation is this P. So you can, if you know this equation, you can transform any entry from this to entry of this using this relation. See.
सर ऐसा करना है कि x u इक्वल टू माइनस के एक्स में x को
हाँ,
pz सब्स्टिट्यूट कर देंगे एंड
exactly.
फिर माइनस के डैश z को कंपेयर करेंगे.
Exactly. I just need somewhere to write. यहाँ पे u इक्वल टू माइनस के एक्स, यहाँ पे तुम pz ले लो, and x is pz.
हाँ सर, दिख गया.
तो माइनस क्या आएगा? This thing you can write as k dash.
k dash.
Z, है ना?
हाँ.
तो याद है ना यहीं पे.
ठीक है, समझ.
जो k dash equal to kp.
ये ठीक है.
So do you get the idea? कि हम क्या कर रहे हैं आज के लेक्चर में, आपने क्या किया, ये आपको आइडिया आ गया. हमने जो डायग्राम में, दिस वाज द मोस्ट इंपॉर्टेंट डायग्राम ऑफ दिस lecture, कि हमने we transformed the system this, and finally when we found a solution we transformed back to the original system to find the original ports. A last note before I end this class, I hope you are using MATLAB a lot now. I hope कि आपने ये startup किया है. Those who have not started yet, I just उनको मैं कहूँगा कि just quickly start using MATLAB because that will be very helpful for you in this course. And what I want to do today is काफी नोट्स यूज कर लिए आज. Not having somewhere to write. हाँ. The last before we end today. In MATLAB there is a command called place. What I would suggest आप क्या करो? The command is used like this. K equal to place A, B, P. Where A is the system matrix, जो कि original system है. Your B is the input matrix, which is your original C, and P is a vector which contains your location for desired poles. यहाँ पे हमारे केस में it was -1, है ना? So if you use this command, you can get K. You will get K जो हमें आज मिला. What was the K exactly? -0.43, -0.513, 517. MATLAB will give you. And the way MATLAB is using this place is the algorithm that I showed you. And one more command is there. That's known as Ackermann's, ABP. Similar experiment. Sometimes this command will fail. Sometimes this command fails if you're having multiplicity greater than 1, which is in our case. यहाँ पे multiplicity हमने poles की same ले ली, -1. What happens? Sometimes this might give you an error. Sometimes. So you can use this command instead. ACKER. This basically means Ackermann's formula. You can find it in books. Syntax exactly similar है. You just store your A matrix, जो आज का question में given था, B matrix, and give the P as your desired poles. You will get K. And the ideology behind these functions is the algorithm that I showed you. Okay? So just try this. Just try this today. Okay, we'll just stop here. Thank you.